Alrighty, so this is the warm-up we did on Thursday, right? So this is kind of the more straightforward one. We have just a straight up phase change, right? Straight up heating and cooling. We're going from a gas at the boiling point to a liquid below the boiling point. So as we can see from my diagram to the right, we're starting at the, far end of the vaporization chunk of the phase change, and then changing phases to a liquid and then cooling that liquid. So we have two Q values to look at. We can see that here we're losing heat, right? We're cooling it off. Heat is leaving the system. Therefore, we know that the answer should be a negative value, a negative heat value, right? So for our two different Qs, right, our first one is a phase change. So we'll use that mass times the change in vaporization, since this is vaporization. Although notice we added that negative sign, right? So you have to reverse the sign because we're not vaporizing, we're condensing. So again, reverse the process, fine, simply reverse the sign on the thermochemical value. Our Q2 is an MC delta T. We have C liquid, so this is liquid water. So we plug in our values. We are given, we're given our enthalpy of vaporization in joules per gram or kilojoules per gram or mole, right? Kilojoules per mole right here. So we're starting with grams, so we have to convert to moles. Then we can use our kilojoules per mole, again, adding the negative. Gets us our Q1, negative 2.62 kilojoules. Then we have our Q2, which uses the liquid specific heat capacity, which is the 1.26 joules per gram degree Celsius. So this answer ends up being in joules. Here we also end up with a negative because we have that negative temperature change. So we have a negative 21,035 joules. We need to have those, the joules and kilojoules in the same units. So we need to convert one of them. I like the tidier numbers better, so we'll convert the joules to kilojoules. So for Q total, we have the negative 262 kilojoules plus the negative 21.0 kilojoules for a total of negative 23.6 kilojoules, okay? So again, always starting with that little picture is gonna be real helpful with orienting yourself. Let's see here. So then, this was the more challenging one I gave you. What does the initial temperature of a 500-gram piece of steel need to be in order to turn 50 grams of water at 20 degrees C into steam at 100 degrees C? Specific heat capacity of steel is given, okay? So we know that, as I'm showing here, negative Q of the metal is going to equal Q of the water, right? It's this heat transfer problem now. This is more like a calorimetry problem. So we want to find T initial of the metal. We know the mass, we know the specific heat capacity, and we know our T final, right? Our T final is that 100 degrees C. So all we really need to do is get Q of the water, then we can solve for T initial of the metal, right? So Q of the water, as we're showing in the picture here, we have two Q values to think of. We're going to heat up our liquid and then we're going to vaporize it. So it's almost just like the other warm-up, but in reverse with a different substance. So Q1 is an MC delta T problem for water, specifically liquid water. Q2 is an M delta H of vaporization problem. This time we do not need to reverse the sign because we are vaporizing it, right? So let's go ahead and just solve this really quick. So for Q1, right, we've got our MC delta T, so our mass of water is the 50 grams. So I've got my 50.0 grams times my C, and it's liquid water, so it's my 4.18. For some reason, that one does not have units. I'm sorry, but it is still joules per gram degree Celsius. And then we need our change of temperature, and we're starting at 20, so there's our T initial, and we're ending at 100. There is our T final. Again, we have that phase change happening still, but that's okay. The temperature change for heating the liquid does end at 100 degrees C. So we'll have our 100 degrees minus our 20.0 degrees, and then we're good. So we will take our 80 degrees, I'm doing a calculator right now, times our 4.18 times our 50. Yeah? Okay, so Q1 is going to equal 16,720 joules, right? Grams canceled and degrees C canceled. So there's our Q1. Q2 is going to be a little bit simpler. That's just going to be the mass times the enthalpy of vaporization. So again, the mass has not changed. It is still the 50 grams times our enthalpy of vaporization, which is right here. So that's times 40.7 kilojoules per mole. But I screwed this up because I need it to be in moles. So there we go. looking at your units, you can see if you're screwing up or not. I was. So I need to get to moles. I know that water, H2O, oxygen is 16, water is each 1. It ends up being 18.02 grams per 1 mole of H2O. Now I can use my enthalpy of vaporization, which is 40.7 kilojoules per 1 mole H2O. See, I've been doing dimensional analysis all along. I just haven't been writing out my conversion factors. So my grams cancel, my moles cancel, and I'm left with those kilojoules. So again, run the numbers. I've got 50 divided by 18.02 times 40.7. And I get 112.93 kilojoules. Okay? Now, does it make sense that these values are positive? Well, it sure does. I'm warming up the water. I'm adding heat. That totally makes sense, right? So now I know that Q of H2O is going to equal, again, I need to get my units to match up, so I'm going to convert my joules to kilojoules. So I've got 16.72, we'll just keep 4, even though I don't think we get that many, plus 112.93. I'll just keep our decimals, why not? We get, I'm going to do math in my head, watch out, 6, there's a 1, 7, so that's 9 and a 2 and a 1. I think that that's correct. 129.65, as long as I didn't screw up my math, okay? So that's my Q of water, okay? Now I can finish, and I'm going to, again, do a little bit of a zoomy weird thing. I apologize if that made the video go bonkers. So now, I know that from up here, right, my Q of metal, opposite sign, is equal to the Q of water. I now have my Q of the water, so I'm going to set this problem up, and I want to solve for my T initial, okay? So again, with my Q, with these equations, I normally like to rearrange them before the numbers are in there, but not once I have to distribute. I'd really rather just put the stuff in. So I'm just going to put all the stuff in. My mass of my iron is 500 grams, right? What else do I need? My C, my specific heat capacity of the iron, is 0.49 joules per gram degree Celsius. Then I have my change in temperature, and I'm solving for T initial, so my T final is 100, just like the water, right? Everything ends at the same temperature. So my T final is 100 degrees C. That's minus my T initial. That's my variable. That's my unknown. And all of this is going to equal the Q of the water as long as I reverse the sign. Again, this negative sign can go anywhere. We can pop it here. Let's just pop it out here, right on, where I had it in the original equation. So there's our negative sign, and this equals that 129.65, and this was kilojoules, okay? So let's start doing some math. So I've got my 500 times my 0.49 times my 100. That gets me that first term. So that is 24500. Again, this is joules minus, let's go, what was that? 500 times 0.49 minus 245 times T initial. Now, I still have to distribute this negative sign, right? So if I distribute it through, this would be a negative and this would be a positive, right? Because I would make the 245 negative. Okay, I think we're good. So keep up with our algebra. Let's add this guy to the other side. But again, let's make it kilojoules so they can all agree. Move our decimal 3 places. We get 24.5 kilojoules, okay? So we get our 129.65 plus 24.5, and that equals 154 that's not a number. Sorry, 154.15 kilojoules equals 245 Ti. All I have to do now is divide, this is not making a good number, divide by 245. Is that right? Yeah? I am right, aren't I? I'm right, I gotta be right. Okay, divide by 245, I think I'm right. Something seems wrong. Okay, let's keep trying. So that number, the 154 divided by 245 equals 0.629. What is my answer in units? Let's see, that is kilojoules, but it also has everything else. It also has grams. Grams are gone, but it has degrees Celsius. That's right. So this is kilojoules per degree C. There we go. So then we get our degrees C over here. So now is the moment of truth, because I never worked this out to get the answer, but does it make sense that our metal's initial temperature would have been 0.629 degrees C? You should all be screaming at your computer screen, no, right? This sample of metal was able to heat and boil a whole bunch of water. I obviously screwed something up somewhere. I'm just wondering what. Let's see here. I'm going to pause you for a minute so I can peek at this. All right, got it. I'm an algebra idiot. You can't add the 24,500 joules to one side and then divide the other side by it. That doesn't make any sense. So let's fix this. See, there you go. Having a sense of what your answer should be can go a long way, because I know that there is no chance that that's my answer. So let's fix my algebra. Okay, so there, what am I doing here? So there's that. So this should equal, I don't know where that number came from. Let's fix all of this garbage. Ugh, gross, I'm so sorry. Okay, here we go. So again, let's try. We're gonna add, and so this should be the 129.65 kilojoules still. There's no reason for that not to be, right? Distribute, yes, okay. So now we'll add our but again, we do want it to be in kilojoules, so we'll make it 24.5 kilojoules. That should still equal 0. So here, I am also gonna add 24.5 kilojoules. Yes, yes, everybody agrees with this? I agree with this, fantastic. Okay, good. So now we have, and we're gonna fix our units on the left-hand side here, but we have on the right-hand side 129.65 plus 24.5, and that's gonna equal 154.15, and that is in kilojoules. Now, on the other side, I didn't carry my units through, but let's check it out. I'm gonna go to a different color for you. So if we're just distributing, right? So it's grams times TI. It's joules per gram degrees Celsius times TI, so the grams, again, will cancel, but our answer for the numbers here, right, so this number value right here is 245, and it would still have the joules per degrees Celsius, and that is times our T initial, right? That's really important, because that is what is going to, that's what's gonna get us our units correct. Now again, see, I just went crazy with my algebra. So now again, we see we have a joules, kilojoules issue. So let's switch this, and we'll put a decimal point in front, and then we'll make this kilojoules. Easy enough, that doesn't affect anything. And then we just divide both sides by 0.24, sorry, that is a 5 kilojoules per degrees Celsius. And we'll notice that our kilojoules will cancel, the degrees Celsius will flip up top, and again, I'm gonna shrink us a little bit. And so, right, so in the end, we are gonna get that 154 value divided by 0.245, and we get an answer that makes so much more sense. 629.18, and again, those degrees C, right, those flip up to the top, so our answer is in degrees C, which it should be. Again, considering sig figs, we only get 3, so we'll kill those, and our answer is 629 degrees C. Sorry about the craziness, but I'm leaving it in. I'm not gonna edit it out, because I think it's super important for you to see how important it is to double check that answer and to make sure it makes sense, right? My work seemed fantastic to me in my head until I saw that answer, and then it was like, whoa, there's no way. And then I was able to spot a stupid algebra error. I wanna get those fixed, so I wanna think about my answers, okay? So there we go, that was that trickier one. Remember, this is more like a level 4 type question, where you have to really pull it apart, know what you're doing, think about a couple different pieces and pull it together, okay? Moving forward, what is this one? Oh yeah, this is one I started you guys on, and I think period 2, I led you guys astray here. You can never just leave delta T as your unknown. I might have told you that you could, but you totally can't. You have to break it apart if one of your temperatures is your unknown, because the delta T's aren't the same, right? The delta T for the metal is gonna be very different than the delta T for the water. We saw that in our lab, right? We had a delta T for the metal of, what, 60 degrees or something, and a delta T of the water of, what, like 2 degrees. So you never get to set your delta T's as the variable. You have to then pull it apart to T final minus T initial and do the distribution like we did in the previous problem. All right, so then we went through the POGIL activity kind of independently, right? I'm not going to go through this. We went through it a lot in class, and we built up these ideas. And then gave you the packets, and I asked you to start working on some problems. So with the POGIL activity, with that inquiry activity, we figured out these ideas of bond enthalpy, these ideas that a bond broken takes energy, needs to have energy put into it, so it would be endothermic, and that would be a positive heat value. And we also saw that when bonds are formed, they're going to release energy, right? Those atoms want to be together. When they get together, they relax, they release energy. That energy is released in the form of heat. Okay, so we went through that. We saw from this guy here, right, we saw that whatever goes on in the middle, all this junk, is irrelevant. All that matters is where we begin and where we end. And this difference here, this delta H, that's where we started focusing in our work on thermochemistry today. Okay, alrighty, so then I gave you the packet, sorry. We jumped in and started going through some stuff. So I cleaned this up a little bit from second period. So second period people pay more attention because this is a little tidier for sure. So the first thing we did was, right, that third activity in the packet that we were working on alluded to these ideas. So this is what's called a potential energy diagram or an enthalpy diagram. You must be familiar with these. You need to be able to interpret them. You need to be able to create them. You need anything and everything for an endothermic or an exothermic reaction with or without numerical values. You need to be able to deal with this diagram. So we see that as written, we always go from reactants to products, right? That's that reaction coordinate idea, the progress of the reaction. And in the y-axis, we're measuring potential energy. The more unstable something is, the more potential energy it has because it'll release a lot of energy as it becomes more stable. We see that from the reactants, and we talked about this, whether it's endothermic or exothermic, you're going to go through this extra peak in energy called the activation energy. And that is to get you through what's called the activated complex. And that is that kind of funky, in-between, unstable state in between reactants and products. It's whatever's going on in the middle, whatever is happening on their way there, okay? So really the things we are most focusing on are the activation energy, the difference between the reactants and the peak of that activated complex, and the enthalpy of reaction, the delta H value. And that is simply the difference between the reactants and products. Specifically, when you're working with a picture like this, it's always products minus reactants. So when we look at this, we see the products are lower in energy than the reactants. So when we subtract those two values, we will get a negative value. It's exothermic. That makes sense when you think about this curve and you think that the products are at lower energy. Where's the energy going to go, right? It has to leave the system. It has to be released, okay? Moving forward, so then we looked at enthalpy of formation, and we talked about enthalpy of formation. We defined here, it's the energy involved in forming a compound. So, and it's, again, from its elements, right? So pure elements have an enthalpy of formation of 0. You use this similarly to bond enthalpies, except with bond enthalpies, you're looking at every individual bond and adding up all the energies. When you're using enthalpy of formation values, instead of individual bonds, you're using the values for the individual compounds, the individual molecules. The other difference is that the data from bond enthalpies is taken from the breaking of bonds. That's the process that gets you those values. So in general, not even in general, always, those bond enthalpies are going to be positive values, right? You have to put energy in to break a bond. Enthalpy of formation isn't obtained from the breaking of bonds. It's obtained for actually forming that specific molecule, right? Another downfall of bond enthalpies is that they're average values. So you're just going to get a rough approximation if you use those. But enthalpy of formation, that is talking about the specific molecule that's listed. So these values can be far more accurate. But you need to remember, those values are obtained from the forming of bonds. So when we do our math, just like with the bond enthalpies, how we had to reverse the sign of those bonds being formed, the ones in the products, here we have to reverse the sign of the reactants because those compounds are not being formed. Those compounds are breaking apart in order to make the products. So you think about what's forming and what's breaking. If we're using enthalpies of formation, you need to reverse the sign of the breaking bonds, okay? Then you just add up all the energies. And when you do that, you get the enthalpy of reaction, the total, the net amount of energy involved in whatever reaction we're talking about. So then another way we can use enthalpy of reaction, so we can calculate enthalpy of reaction, we can also use knowing the enthalpy of reaction in order to figure out an unknown enthalpy of formation. So take my A, B, C, D, right? We know enthalpy of formation for A is 22, B is 30, C is 15. We don't know it for D, but we do know that the enthalpy of reaction is negative 30. So I know if I add up all my energies, it should equal 30. So again, I do my analysis, what's breaking and what's forming. The things that are forming, I do not have to reverse the sign because I'm using enthalpy of formation values. However, the reactants, because those are breaking apart, I do have to reverse the sign, so I add that negative. Then I just add everything up and set it equal to negative 30. Now I have my variable there, so all I do is algebra, right? So here we see I do my algebra, and we get an answer that the enthalpy of formation for compound D is 7, okay? So we can use it in that. C. We also saw, what's this one? Oh, so here again, I'm using enthalpy of formation values to calculate that enthalpy of reaction, right? So again, reverse the sign, we go through, we can get to an answer. Did I get you? Okay, I didn't. All right, so let's just, did I not get you to where? One more little thing. Let's say I have A plus B makes C, and my enthalpy of reaction is 52 kilojoules, why not, per reaction. Oh, and let's make this, we'll put a 2 there, let's put a 3 there, okay? So, what if my question was, you have excess A and 5 moles of B. How much energy is needed for this reaction, right? I say needed because I see that it is an endothermic reaction. So I know that that energy is going to be going into it, okay? So this is now where we're blending our stoichiometry skills with our understanding of how we can use thermochemistry. So the first thing to recognize is that this guy right here, my enthalpy of reaction, that's also a conversion factor, right? This could be 52 kilojoules per 1 reaction. We could do that if we wanted. Or we could look at our reaction and say, all right, or it is 52 kilojoules per 3 moles of C. Or it is 52 kilojoules per 2 moles of B, right? Or 1 mole of A, or whatever, right? So we can turn that value into any number of conversion factors however we want to do it. So I've given us an easy one. We don't have to do limiting reactant. I'm going to start with what I have, and I have 5 moles of B, okay? Then I want to know how much energy is needed for this reaction. So I don't even have to go to my products here, right? I know I'm going to use 5 moles of B. I know that for every 2 moles of B that are used, I'm going to release that 52 kilojoules. That's the relationship, because the 52 kilojoules is for 1 reaction, and in order for 1 reaction to happen, I'm using those 2 Bs. So I know that it's 2 moles of B to use, I'm sorry, not release, to use 52 kilojoules of heat. So, right, I chose to use this one. Now my moles of B cancel. I have a number, I don't know what it is, but I will find out for you. 5 times 52 divided by 2 equals 130. So I will need to put in 130 kilojoules of heat in order for this scenario to take place. Okay, so I think it's the second full page, so the third worksheet in that packet has mostly problems like this, where you're combining what you know about stoichiometry and how to use those skills with using the enthalpy of reaction. The trick here is recognizing that enthalpy of reaction, if it's just a delta H values for a specific reaction, it's referring to each reaction that happens. If you want to get it into moles of a reactant or a product, you have to look at the balanced chemical equation. Okay, we're going to leave it at that for now. Keep practicing, keep working it, and you'll get it there.